I am now with Katie Mulrey, who is a PhD student at the University of Delaware. Am I?
Yes, that's right.
Wow. Okay, I remember. And she recently got back from Antarctica, where she was a part of the Anita Free team, and they launched successfully not long ago. And this is all very fascinating. So she was very kind and agreed to join me and for a short interview. So hello, Katie. Thank you for being here. I am doing this interview on behalf of a space internet show that I am part of called The Spaceship. So to all of you who will be watching this, since we're not showing this live, hello. And I'm sorry this is in English, but Katie, I assume, doesn't speak Hebrew.
Nope.
So we will have this explained later on. So Katie, why don't you tell us a bit about yourself? How did you get into astrophysics? What exactly do you do?
Okay, sure. Like you said, I'm a graduate student at the University of Delaware. I'm in my 7th year of school, so I've been there for way too long. And I chose the university because I knew they had astrophysics program, and when I started it, I didn't really even know what that meant. It just sounded like a fun thing to do. So I decided to go there, and it turns out I really like it, so that's good. It could have gone the other way too. So I spent a couple years in classes, and then a couple years working on other projects. And then in the spring of 2013, I joined Anita because it was timing out quite well. Anita's this balloon project, and it was the experiment had just happened, so it worked out well, like timing with my thesis and everything like that.
Wow, that's great. How did you get into astrophysics? Except for were you interested in this at all before, or did you just happen to find it interesting at that point and then went into it?
Yeah, when I was kind of through my whole life, I've just found astronomy and astrophysics the most interesting thing. If I think about what field could you possibly think is the most interesting, it seems like astrophysics, the highest energy particles in the universe. It doesn't get much better than that. So I never made a conscious choice I want to do astrophysics, but everything kind of led in that direction, and then ended up there. So
cool. So maybe you could tell us a bit about the experiment before we get into the nitty-gritty, but just what it is, how did you get to be a part of it?
Sure, yeah. So ANITA is an acronym for, let's see if I can do it, Antarctica Transient Impulse Antenna, which means that it's a balloon with a bunch of antennas on it, and what it's searching for is a signal from cosmic rays and neutrinos coming from outer space. So first of all, I didn't really know what a cosmic ray or a neutrino was a few years ago before I started school. So cosmic rays and neutrinos are particles that come from outer space, from supernovas or active galaxies, things like that just have a huge amount of energy. And we're looking for the highest energy ones that anybody has ever seen. So if we can detect these particles, it tells you a lot about what's going on when stars explode, and just fundamental things that nobody has any idea about right now. So when those particles come into the Earth's atmosphere, they're flying all around space, and some of them hit the Earth. They give off some radio waves, and then that's what we're detecting with the antenna. And this is a group collaboration based at the University of Hawaii, and they have a bunch of different schools, 10 different universities work on it, and the University of Delaware happens to be one of them, and my advisor works on their project, so I just said I'd like to do that, and that's how I got to be with Anita.
Wow, that sounds way too simple. So maybe you can go into it a bit now. I was wondering, you talked about detecting the radio signals. those directly from the particles hitting the ice in Antarctica, or are those from chain reactions and then the chain products actually hitting the ice?
It's sort of a combination. Neutrinos and cosmic rays we actually detect a little bit differently. Neutrinos don't interact with very much because they're not charged. So they are traveling through the Earth, up through the ice in Antarctica, and if they get close enough to a particle in the ice, for example, they'll transfer their energy to that particle, and then that starts it kind of explodes in into like you said, a chain reaction of, like this particle has tons of energy, it hits another particle, now there's two particles, and then those go off and hit particles, and so it just blows up, and soon there's billions of particles, all with high energy, and because the charges are different, like this side of the particles has a different charge than this side, that creates the radio waves, essentially. And the cosmic rays is a similar thing. It just doesn't happen in the ice. It happens in the air. But it's not directly the cosmic ray. It's the shower of particles that come from it.
So you're getting for cosmic rays, you get the radiation directly from the air.
Yeah, cosmic rays are charged, so they wouldn't be able to make it through the ice. They only get a little bit into the atmosphere before they blow up into all these different particles, basically.
So the neutrinos are actually the ones coming from the other side of the Earth, or do you also expect some to come from directly above?
Well, there are plenty of neutrinos coming from above, but the problem is that when they're in the air, the chance that they interact is so small. The reason that we use the ice is because it's more dense, and so that it just has a better probability of reacting. And even in the ice, there's a pretty small probability. Oh, now here's my cat. That the neutrinos are going to interact.
Well, I mean, I guess that's why we assume there's billions upon billions, and therefore we expect to detect a few, right?
Yeah, exactly. And that's why we use Antarctica and the balloon. One of the classic problem with neutrino detection is that they're hard to see, and I forget the figure, but it's something like if you have a square kilometer, for the energy that we're detecting, a square kilometer detector, you're going to see one a century or something like that. So it's not practical to build a detector. So instead of building a detector, we're using the whole continent of ice as a detector.
That is really cool. So big. That is really cool. I remember that you mentioned in the email that, I mean, this is Anita 3. You mentioned that Anita 1 and 2 weren't actually meant to detect cosmic rays and neutrinos. Mm-hmm. Right? What were they planned for?
Anita 1 was just supposed to be neutrino detection, because that's the whole point of being in Antarctica. And so when they were analyzing the data, they found all these other pulses that looked like neutrinos, but they weren't neutrinos. They weren't coming from the right direction, and they had a different polarization. And it took years to figure out what they were, to kind of pinpoint it, because it was a mystery. And then they said, oh, of course, we can see cosmic rays too. It's the same mechanism. But by then, Anita 2 had already happened, and they had already kind of tuned the detector not to look for that sort of thing, unfortunately, because now they realized that was a huge signal. So then Anita 3 is now officially looking for both cosmic rays and neutrinos.
Okay, you mentioned tuning the signal out of the detector. Mm-hmm. I remember you wrote that the detectors are so sensitive that you have to be careful and tune out lots and lots of noises. How is that done? Do you use data from previous Anitas, or just reading now?
It's kind of a combination. Part of it is done in the electronics. Most of it is done in the analysis. We have these antennas. They detect both horizontal and vertically polarized radio waves. And then all the electronics have filters to kind of detect just the frequencies we want and everything like that. I guess the important thing is that the signals are so small that the whole instrument can't even be turned on or really tested until it's like in the air above Antarctica, because like a cell phone, for example, would just like ruin the electronics. It's way too strong a signal. So the signals that we see are so tiny that so the detector's just super sensitive. But the way we pick out the cosmic rays and the neutrinos is mostly in the data processing. Most of what you see is just noise, so you'll just see like a wave of just kind of like nonsense noise. And then every once in a while, you'll see like a sharp signal, really small, like a nanosecond wide. And we have all these different antennas, right? And if the signal lines up the same way in all the antennas and the timing is right, that's how you determine that you saw something. And then you also have to worry about like pointing, like if we fly past the South Pole, there's tons of radio signals coming from there. So any signals that we have that point back to the South Pole, we throw out, and just like that with all the other bases we go by.
So out of all the data you get, only a very tiny fraction will actually be used or have any meaning.
Yeah, exactly. For NIDA 1 and 2, I think they do simulations first to figure out how many neutrinos they expect based on how long it was flying and how sensitive everything was. And it's like flying for like 40 days, you expect 1 or 2 neutrinos, you know. So it's like really, they're really rare. And maybe like 100 cosmic rays or something.
Oh, wow.
Yeah.
And so is ANITA in the air now, or did it already land?
It actually landed a little bit prematurely. It landed on, let's see, January 9th, I think. We were hoping to get, so we launch it, and it gets caught in this polar vortex around the South Pole, and so it usually just flies in a circle. We wait till the wind's set up around Antarctica before you launch to make sure it's going to go in the circle around Antarctica. If it would fly off over the ocean or something, you don't want that to happen because you want to be able to recover the hard drives. Some of the data is sent back through satellites and telemetry, but there's just not enough bandwidth to get enough data. So most of the data is on the instrument, so you want to have it land in a place that you can access it. So the NASA people who are tracking this thing always have that in mind. So a couple, I guess it was around the 9th, ANITA had made one full loop around Antarctica, and it was heading on its second, and it kind of like was heading towards the coast, and they're like, all right, cut it down, you know, because it was about to go out over the ocean. But we got a 22-day flight, which isn't bad. So there should be some good data, and it was more sensitive. So we're actually they're collecting the hard drives right now, like in real time, and sending those back to us. So we'll have the data.
That's cool. How did they cut the balloon down remotely?
Yeah, so they have you can send controls to the instrument. They have some satellites on there, so you can send very basic controls like on, off, this or that. And there's like there's the balloon, and then the balloon is attached to a parachute, which is attached to the instrument. And there's a little lever between the balloon and the parachute that you can just chop, basically. So the balloon just goes flying off into the sky, and then the instrument and the parachute come down to Earth. And even though there's a parachute on there, it's a pretty violent landing. You know, it gets. We just got a picture.
That was what, about 2 tons of equipment?
Yeah.
Wow. Yeah. Very big parachute.
Yeah, it's a very big parachute, and it still gets pretty smashed up when it lands. So, yeah.
Right. So let's talk a bit about life in Antarctica. I mean, that sounded really exciting.
Yeah, it was fantastic. I was staying at the American base called McMurdo Station. It's kind of like a little college town almost. It's a strange place. I think there were at the maximum in the summertime down there, which is right now. There are about 1,000 people. Probably about 700 that are stationed at McMurdo, and then there's lots of people that come in and out of McMurdo on their way to the South Pole or other things like that. Most of the people are not scientists; they're support staff. So I didn't realize how much support was required. I mean, I guess it's obvious, like running a little town, but there's cooks and drivers and fuel people and carpenters and maintenance and all that. And then there's the scientists. You have people like studying seals and penguins and geology, and there's just kind of all sorts of stuff going on. But yeah, it's basically like being in college again. It was like you live in a dorm, you have a roommate, you eat in a cafeteria, you know, there's like movies and stuff like that. So I think the weirdest thing was that since it's summer there right now, the sun never sets. So from the time I got there until the time I left, it was just like daylight all the time. It's really strange.
So you have to have really good light isolation, I guess.
Yeah, and even then, like, you wake up, I don't know, the first couple weeks I was there, I kept waking up in the middle of the night, and, like, you can still see that it's kind of light out, and you're like, oh, no, I slept in.
Oh, wow, yeah. I guess I never thought of that. I guess that's a really scary thought when you wake up and, like, do I have to be somewhere?
Yeah, and we went to this, they have the balloon facility, which is like 7 miles away from the town, so there's like one bus that goes there, and if you miss the bus, that's it for the day.
Right. So I had a few more questions. Oh, right. So I heard of this whole expedition and of you because you wrote a few columns for Scientific American. Mm-hmm. How did that happen? Did he contact you, or?
Well, actually, my best friend from high school is an editor at Scientific. Not the blog, not that section, but I guess they were having a meeting, and they didn't have enough science blogs going on. There was going to be like a lull or something, so she just said, "Oh, my friend's doing this," so it was just totally like that.
Well, are you happy about the chance? Do you like the idea of doing popular science and writing for the masses, or?
It was really fun, and having to write things in a way that kind of like stepped back from the experiment was really good for me. I think I understand it better now. Having to just describe it in normal terms without using all the jargon and stuff, it made me actually think about it and understand what I was actually doing a little bit better.
That's great. Do you keep a blog? Do you think you'll keep writing about other things, or?
Yeah, I hadn't had a blog before. This was the first time I've ever done anything like that, and I just really enjoyed it. So I don't have one now, but I'm planning on starting one to just continue. I didn't realize, like, I think people actually really like reading about it and hearing about it because it's just kind of interesting.
Oh, yeah, we're finding this out as well. No, it's really fun because I started just writing a few things on my Facebook page, and people liked it, and it turned out into a blog and an internet show, and it's just fun. There's a lot of interest, and so keep us posted, and I'll definitely tell people about your blog. I'll be reading it for sure.
Oh, thank you.
So, Katie, thank you so much. Don't go. I'll turn off the broadcast, but just so we can say a few more words. And do you want to say anything to our viewers before we're done?
Oh, well, thanks for listening. I hope it was interesting. And
it was fascinating. All right, thank you so much.